In the last episode of this series, we left our little astronaut able to walk on a line of tiles. Now we have some kind of platform with a pickup on it. But the player cannot reach it, so let's add jump logic to our player controller. But wait, with already two if statements in place, our code could already get messy. The more possible actions you put in your player controller, the harder your code becomes to read. This is because more and more if-then statements are needed to keep your possible player states apart from each other. That is spaghetti code. And it is in no way a healthy nutrition for a programmer. The solution I will present you in this video is a basic state machine. The decentral approach will avoid putting all the player logic in just one messy script. We will have a fixed set of states, namely idle, run and jump, and our player can only be in one state at a time. We also will have transitions between states, and these transitions will be triggered by certain input events, namely keys, or parameters like the player velocity if they reach a certain value, represented by the green arrows. You can build on this concept to create your very own combination of states. Sounds good? Let's go scripting! Let's start by creating a new state space class script. All player states will derive from this base class. It consists of 4 simple functions. Entering the state, the commands in the enter function will be executed. And after that, the logic function will be called for each frame. Most of the states will check for player input. That's why we need a getInput function. And last but not least, the getTransition function checks if there's a transition for a next state. For our functions we need 5 variables in the state class. A reference to our player kinematic body 2D, a dictionary containing all the states the player can be in, jump and direction variables for our getInput function, and in case of a transition we need to return it in the next state variable. The next state variable is the return value of our getTransition function, and it is set to null each time a new state is entered. And now it's time to create our first state. What's easier than to start with a state where nearly nothing happens? In a new scene, add state as a child node and extend the script. Idle state will inherit from our basic state class. Here we override our logic function from the state class. First we call the state class's logic function. Then we check if our player kinematic body 2D's velocity is not equal 0. So next state will return run from our states dictionary. If however jump is true, we will of course return jump state from our dictionary. Returning from idle to our base class, it's time to write a few more lines for the functions. The state class will also control movement and animation for our player. We call the player's animation function inside the enter function, the move player function inside the logic function, and the physics function inside the getInput function. These functions do not exist yet, but soon they will. Inside the input function we also check for jumping and horizontal movement. Please make sure that your keys are defined accordingly to your project's input map. We still need to set the object reference for our player kinematic body 2D and fill our states dictionary. This will be done by building our final part, the state machine script itself. We create a new state machine script which will be like a service script for all our states. We also give it a class name like we did with the state script before. So we can find it in the create new node dialog in our Godot editor. In the ready function we wait until the parent, which is our player node, is ready. Then we loop through all of our child states, which could be idle, run, jump and many more. They are stored in a dictionary, and this dictionary is passed in another loop to all of the states. The state machine should always be aware of which state the player is currently in. So we assign this state to a variable current state. Let's assume that idle is the first state your player should be in. So the first state we assign to current state is idle. The enter state function of our state machine calls current state's enter function. We currently do not override the base states class's enter function in idle state. That's why the only thing done here is setting next state to null and calling the state's animation from the player node. More interesting stuff goes on in our state machine's physics process function. We call current state's logic function and check for conditions that trigger a change to a next state. This next state becomes the current state in the change state function. And once again, the enter state function is called. Okay, we can now finish the basic construct of our state machine scene. Thanks to our class name, we can add a state machine node directly in the editor. Let's make it root and rename the state node to idle. And we finish this step by saving our state machine scene. But we still have to make some modifications for the player script we built in the first part of this series. This is due to the fact that our state scripts now gain direct access to our player script. And because we get the keyboard input now from the state itself, no longer from the player script. That's why we rename getInput to calcPhysics function. No more need for the getInput in the physics process function, so let's delete it. And also the left and right bools and the associated input events are no longer of any use. The current state will also pass the float dir to this function, setting the player's x velocity. That's why in the modified player script we check for the velocity's negative or positive value. Depending on this comparison, the player sprite is either flipped or not flipped, and run speed is added or subtracted to the player's x velocity. And the two other functions currently called from our state will be movePlayer and animation. As movePlayer will take over the move and slide from physics process is currently passed. Final steps are to instance our state machine as a child scene in the player scene, hit play and say hello to a bunch of happy bugs. In the state machine script itself, I put too many indentions or tabs in the physics process function. I also used pull instead of player as a kinematic body 2D in the state script. Looks I did this also in the idle state script. And I wrote fun where it should be funk. And the dictionary in the state machine script must be named states instead of state. I did this 2 times. For some unknown reason, I commented out the call of the player animation in the state base function and missed a first call to the enterState function when ready in the state machine script. The rest of unexplainable error messages might be due to quantum fluctuation or some magic swapping over from parallel universes. So it's always a good idea from time to time to simply restart the Godot editor. Bugs killed? Looks like everything is perfect now. Really? I hear you say. So much time of programming just to put our astronaut in idle state? Something we accomplished with a simple player controller in 2 minutes? Yes, but from now on, things will get a lot easier. We can install run state by adding a child state node in our state machine scene and call it run. First, we extend the state class script. Second, we call the logic function of the state class and check if our getInput variable dir is not equal 0. If so, we third assign idle state from our state's dictionary to next state. And of course, we have to fourth implement getInput and the logic function of our state base class. And fifth, write calcPhysics correctly in the getInput function. But that's all we need to implement running behavior in our new modified player controller. Now let's quickly implement jump logic in the last 2 minutes. Run and idle state, check if jump is true, and if so, get transition function from the state class returns jump state as a next state to the state machine. I already added a very quick jump animation in the player scene to its animation player. It consists of only 2 frames, does not repeat and has length of 0.4 seconds. We then add a state child node to our state machine scene called jump. In the attached script, we call the base class's logic function and return idle state if our player kinematic body 2D is on floor. We also have to override the enter function here. We call the base function, which sets next state to null as we know, and call player controller's jump function. Only thing left to do is to make minor adaptations to our player controller. We need a variable gravity of course, and a jump speed which I set to 200 pixels. Physics process is now used to calculate our y velocity, and we create the jump function, which checks if the player is on floor, and if so, subtracts jump speed from velocity. Tiny Astronaut now can easily reach the platform and quickly grab his hard-earned rocket. But this is another story, which I will teach you soon. Thanks for watching and for waiting. Stay safe and happy Godoing.